Let's talk about secrets. Your secrets. From your bank details to your private messages, so much of our lives are lived online, and we just trust that it's all kept safe. But what does that actually mean? What's the lock and what's the key in this digital world of ours? Well, today, we're going to find out. It really is a simple question, right? But the answer is a fascinating story. It's a story of some seriously clever mathematics, incredible engineering, and a global standard that protects billions of people every single day. We are about to pull back the curtain on the magic of modern encryption. Okay, so take a look at this. On the left, you've got a simple image of a penguin. No big deal. But in the middle and on the right, that's the same image after it's been encrypted. Here's the catch, though. One of those is a catastrophic failure that basically leaks the image's pattern, while the other is perfectly, totally secure. By the end of this, you're going to understand exactly why that is. To solve the mystery of the penguin, we first need to get a handle on the sheer scale of the challenge. I mean, just think about your average day online. We're not just protecting one little secret, we're talking about a constant, massive flood of sensitive data. Every single time you send a secure message, check your bank balance, or even just browse a website with that little padlock icon up in the corner, you are putting your trust in the hidden world of cryptography. It is, quite literally, the invisible armor of our digital age. So what does this invisible armor even look like? Well, modern cryptography isn't just one single thing. Nope, it's a whole family of different tools, each one designed for a very specific job. You can think of it as having three main branches. You've got asymmetric encryption, which is really cool. It uses a public and a private key. Then you have hash functions, which create these unique digital fingerprints for data. And then you've got the workhorse, the one we're going to focus on today, symmetric encryption. You know, the concept here is actually beautifully simple. Imagine you and I share the exact same secret key. I can lock a message in a box, send it over to you, and you can use your identical key to unlock it. Simple, right? It's fast, it's super efficient, and it is perfect for encrypting huge amounts of data. And when we talk about symmetric encryption, there is one algorithm that absolutely rules them all. It's called the Advanced Encryption Standard, or as pretty much everyone calls it, AES. Now, AES isn't just popular, it's the official global standard. Since way back in 2001, it's been the go-to encryption method for the US government to protect classified information. And yeah, it's also used by pretty much every major tech and financial company on the planet to protect your data. So how does this thing work its magic? Well, at a really high level, AES grabs your data, chops it into blocks, and then puts each block through these intense rounds of transformation. It substitutes bytes, it shifts rows around, it mixes up columns, and then it mashes it all together with a piece of the secret key. Think of it like taking a deck of cards and giving it a ridiculously complex mathematical shuffle, and then doing that 10 to 14 more times until the original order is just gone. It's statistically indistinguishable from random noise. And that is why we have so much confidence in it. See, AES was the winner of a massive global competition. It has been relentlessly attacked and analyzed by the world's best codebreakers for decades, and to this day, no practical attack has ever broken it. I mean, to put its strength into perspective, trying to guess an AES key by brute force is like trying to guess one specific atom in the entire known universe. It is a digital fortress. Okay, so if AES is this unbreakable fortress, that brings us right back to our penguin problem. How could something so incredibly secure fail so spectacularly? Well, the answer isn't in the lock itself, but in how you use it. And this right here is the crucial point. The strength of the algorithm, AES in this case, is only one part of the story. The way you actually apply it is every bit as important. And here it is, the big reveal. The reason you can still see the penguin in that middle image is because it was encrypted using a method called electronic codebook mode, or ECB. And ECB has this one fatal flaw. It encrypts identical blocks of data, like say all the white pixels in the background, in the exact same way every single time. And that's what preserves the original pattern. This introduces a really critical concept, the mode of operation. Think of AES as the powerful engine in a car. The mode of operation, Well, that's the transmission. It's the set of rules that tells the engine how to actually handle the whole journey, not just one turn of the wheels. It's the recipe for how to encrypt a whole stream of data, like a big image file, block by block by block. So here's the difference, plain and simple. The bad mode, ECB, it's kind of lazy. It just encrypts each block on its own. But the good modes, like the one used for that perfectly scrambled image, they're smart. They use clever techniques, like chaining the result of one block into the next one, which guarantees that even two identical blocks of data will produce completely different encrypted results. And that is what gives you that secure, truly random-looking output. So let's zoom out, because this brings us to the big picture. Real security isn't just about one algorithm or one mode. It is all about building layers of trust, starting from pure mathematics all the way up to the apps you use on your phone. What you're looking at here is basically the blueprint for all of modern digital security. It's a stack. It's like a cryptographic skyscraper, where each floor relies completely on the one below it to stay standing. At the very bottom, you have the bedrock, the foundation, pure math. On top of that, you build the framework, which is the specific algorithm and mode, like AES in a secure mode. That framework is then used by a protocol, like TLS. That's the language your web browser speaks to make secure connections. And finally, way up at the top is the application you actually interact with. Every single layer is absolutely essential. And that really is the key takeaway. When you see that little padlock in your browser, you're not just seeing one thing. You are seeing this entire, deep, robust system of trust with all its hidden layers working in perfect harmony just to keep you safe. So, no, it's definitely not magic. The security you and I rely on every single day is built on decades of hardcore mathematical research and really rigorous engineering, done by brilliant people all over the world. Which, of course, leaves us with one last, absolutely fascinating question. AES is a fortress built to withstand today's computers. But what about tomorrow's? With things like quantum computers looming on the horizon, the race is already on to build the next generation of cryptographic standards. Because the work of keeping our secrets safe, well, that work never truly ends.